All right. Now for another free response all about torque. So, suppose a group of students are decorating a Christmas tree with ornaments. They notice that in order for one of the tree branches of mass 2m and length L to support an ornament of mass m on its right end, a horizontal supporting string is required. In this scenario, the branch makes an angle theta out the horizontal. All right, so we're in a static equilibrium right now. So as such, first thing we want to do is find an expression for the force of tension required to keep this system at rest. So if we did a free body diagram here, we have the weight of the branch itself, we have the weight of the ornament, and we have a tension force. But also, the thing that makes this non-trivial is that we also are going to have some mystery hinge force acting at that pivot point. So as such, if there's a force that we strongly dislike and do not need to calculate in our problem, we can remove it by choosing that to be our pivot point. So we are going to pivot right here, because if distance is 0, there's no torque. So that eliminates the need to include this hinge force in there. So we have 2mg right there. We have mg right there. And we have some unknown tension force acting up there. And we're just going to ignore the hinge force because it doesn't matter for our purposes. Derive an expression for the force of tension in the horizontal cable, assuming the system remains at rest. So, remains at rest means that the sum of the torques have to be 0. So this means that the counterclockwise torques have to equal the clockwise torques when we add them all together. So let's figure out how to actually do that. So since we're dealing with horizontal and vertical forces, it really looks like lever arm is probably going to be our best option here. So I'll get rid of that because it's going to just clog stuff up. So again, we know that the torque, which is equal to R cross F, can also be written as R perpendicular times F. And this is called the lever arm. And it's just the shortest perpendicular distance from the pivot to the line of action of the force. So this basically says, what's the shortest distance perpendicular to the force that gets you to the pivot? So in this case, for the 2mg, we're looking for this as our lever arm right here. And we can see that this is going to be L over 2 times cosine theta. Because the mg force is acting a distance of L over 2 up the rod. And this is therefore just L over 2 cosine theta. So we have two counterclockwise torques. We have the 2mg and we have the mg. And those together have to balance the clockwise torque of the tension. So just going through lever arms here, so we can see that if the center of mass is L over 2 away from the pivot, that's going to make the lever arm the perpendicular line between the vertical and the pivot. So again, it's just going to be the horizontal distance. So we have a force of 2mg with a lever arm of L over 2 cosine theta. Then, by a similar argument, you can see that mg is going to have a lever arm of L cos theta. And those two together have to equal the tension force times its lever arm. So let's figure out what that is. Well, the tension force is actually horizontal. So we're actually just looking for a vertical distance here. So we're actually just looking for the shortest vertical distance between the tension force and the pivot, which is just going to be this distance here. And I should have actually just reversed the orientation right here. Okay, so we want to find what that is. Well, if this angle's theta down here, that makes this angle theta. And if the hypotenuse of this triangle is L, because the tension's L away, this is going to be L sine theta. So the lever arm of this one's L sine theta. Notice L cancels from everybody. And this 2 actually cancels with that 2. So we're just going to get mg cosine theta plus mg cosine theta is equal to ft times sine theta. So we're just going to get ft is equal to 2 mg cosine theta divided by sine theta. But cosine over sine is just cotangent. So this is just 2 mg cotangent theta. So kind of a tricky little derivation there. But that gets us our tension. All right, now we've got a simpler case. We've just moved the Christmas tree to a horizontal orientation, but they notice that this is actually unbalanced and generates an angular acceleration. So we're actually just going to want to derive an expression for the initial angular acceleration of this system. So once again, we're just going to use torques, but it's actually much easier this time because there's no angles to deal with. So this is still 2mg, and this is just mg. But now we can just take their actual distance because the lever arm is their actual distance. Because again, if the force is vertical, then the lever arm is going to be perpendicular to that, so horizontal. So we're just asking, what's the horizontal distance between the pivot point and each of those forces? Well, it's just their actual distance. So angular acceleration from torque, we're going to have to use that net torque is equal to I times alpha. So let's start just by finding the net torque. So the net torque is just going to be the torque caused by the 2mg plus the torque caused by the ornament mg. So for the rod itself, we have a force of 2mg acting L over 2 away. And then for the mg, we just have that force acting a distance of L away. So we actually get 2 mgl. So net torque is just 2 mgl. But then we also need to find the moment of inertia of the system. So the moment of inertia of the system is going to be the moment of inertia of the rod plus the moment of inertia of the ornament. So a rod, well, it has mass 2m, so it's just going to be 1/3 times 2m times L squared. And then the ornament, it has mass m as a distance L away, so it's ml squared. And just working this out, you can see that we're going to get 2/3 ml squared plus 3/3 ml squared, so 5/3 ml squared. So that's our torque, that's our moment of inertia, so we can just set 2 mgl equal to 5/3 ml squared times alpha. And after a bit of algebra, you can see that alpha is going to be, well, let's see, the mass cancels, and also one of the L's cancel. So alpha is just going to be 6/5 times G over L. As the branch swings towards its vertical position, does the magnitude of its angular acceleration increase, decrease, or stay the same? So if we think about it, Angular acceleration is caused by torque. So if my rod goes from horizontal to vertical, notice that the mg starts at the maximum possible perpendicularity, and it ends with parallel. So at the start, this is actually the maximum torque that's going to exist on our rod. So the alpha is actually going to decrease. Why? Well, because as the rod swings, less of the weight is perpendicular to the rod. So what this does, this creates less torque, so generates less torque, since torque is equal to R times perpendicular force component, and thus less. And thus alpha is lower as the bar swings. Derive an expression for the center of mass of the rod ornament system. Well, this is actually pretty straightforward. We're just going to apply the formula. So center mass is just 1 over the total times the sum of each of the masses weighted by their coordinates. So we have 2m plus m in our system. And then we have a rod of mass 2m, whose mass can be thought of as being L over 2 from the end, because it's uniform. Plus the ornament, which is a mass m, but located all a distance of L away. So from this, we're going to get 1/3 times 2 times m plus m, which just 1/3 ml plus ml. So we get 1 over 3m. So we get 2/3 L as the location of the center mass. Suppose the rod's released from rest. Solve for the final linear velocity of the ornament as it passes through a vertical orientation. So we unfortunately cannot use kinematics. So alpha is not constant. So this means no kinematics. So no omega f squared equals omega naught squared plus 2a theta. We have to use energy here. So all we're going to do is use conservation of energy. So we're just going to set U at the top is just going to be equal to K at the bottom. And we want the linear velocity of the ornament, so we are going to have to sub out some quantities here. So U at the top, well, we have 3m times G times H of the center of mass. So again, it's important to look at how the center of mass is changing height, not the whole thing, because everything on here displaces a different height. So this piece, a little bit of height, but the ornament does the entire length of the rod. So we have to figure out what that's doing. And then KE at the bottom is just going to be 1/2 times the mass of the system, or sorry, times the moment of inertia of the system times angular velocity squared at the bottom. So for the height of the center of mass, we said it's at 2/3 L. So if we actually track that, you can justify that every point on the rod displaces its distance from the left end. So the right end goes all the way down L. If you're halfway, your height changes halfway. So this is also going to be 2/3 L on that side. So the center of mass of the rod falls by 2/3 L, because I just tracked where the center of mass is actually falling. And then we said the moment of inertia of the system was 5/3 ml squared. Multiplied by omega f squared. And now we're just going to do a bunch of simplifying. So let's see, we'll cancel the 3's. So we get 2 mgl is equal to 5/6 ml squared. But then we can sub out omega for V over L, since we know omega is equal to V over L. So that's going to cancel. That's going to cancel these L's. And also the M's cancel. So we get 2GL equals 5/6 V squared. Or V squared equals 12/5 GL. And notice our units did in fact work out properly, because we get V equals square root 12/5 GL. Because again, if this was just a thing falling, it would be root 2GH. We got a different result here because of the rotational inertia, but the units still work out to units of velocity.